Hello everyone. In this video I'm going to talk about Coulomb's law and its applications. Coulomb's law talks about the kind of force that will be experienced between two charges when placed at a certain distance apart. Now, say that Q1 and Q2 are the two charges that is placed at a certain distance apart. Now, this law says that the force between these 2 point charges, force between two-point charges is, number one, directly proportional to the product of magnitude of the two charges. That is, F is directly proportional to Q1 into Q2. Suppose let's say that's equation number 1. And number 2, inversely proportional to the square of the distance between the charges. Now, if these 2 point charges Q1 and Q2 are placed at a distance r apart, then the second one says that F is inversely proportional to r square. Question number 2. Now combining 1 and 2, we have F is proportional to Q1 Q2 by r square. Now we note that this force, it acts on the line that is joining the two charges. So if this proportionality is converted to equal sign, there will be a constant. So I write here K is the constant. K is the constant of proportionality. So K times Q1 Q2 by r square, where this K is found out to be 1 by 4 pi epsilon naught. Here epsilon naught is the permittivity of free space. Also, the value of K is calculated to be 9 into 10 to the power 9 Newton meters square per Coulomb square. Now let us suppose that if these are the two charges Q1 and Q2, and let us say that both of these charges are opposite in nature. For example, one is positive and the other one is negative. Then there is attraction, so they come towards each other. Whereas, if both of these are like charges, as in Q1 is positive, Q2 is also positive, then what happens? They tend to go away from each other because like charges repel. It means This is Q1, this is Q2. So the force will act outwards. But in any of this case, the forces acts along the line that joins the two charges. So when we talk about like charges, since they move away from each other, therefore the force acting between them will be in outward direction. But when we talk about unlike charges, the force experienced would be in the inward direction. The next one is SI unit of charge. SI unit of charge. Now the SI unit of charge is Coulomb, which is also denoted by C. Now what is 1 Coulomb? We'll write down 1 Coulomb is a charge that when placed at a distance of 1 meter from another charge of same magnitude in vacuum experiences an electric force of repulsion of magnitude 9 into 10 to the power 9 Newton. Now the next one, principle of superposition. Principle of superposition. This principle of superposition states that the total force on a given charge due to a number of other charges is the vector sum of individual forces exerted on that charge by all the other charges. Let's write it down. Total force on a given charge due to a number of other charges is the vector sum of all the individual forces exerted on that charge by all the other charges. Now, let's look at this way. Suppose this is your Q1, this is your Q2, this is your Q3, and so on. This is your nth charge, Qn. Let us suppose that these are some of the charges, Q1, Q2, Q3, and so on up to Qn. So we have multiple charges. Now let us suppose that we have to find out the total force on this Q1 due to all of these charges. So how will we calculate? So this principle states that the total force on Q1 will be the vector sum of the force on Q1 due to each of these charges. That means force on Q1 due to Q2, force on Q1 due to Q3, force on Q1 due to Q4, and so on, force on Q1 due to Qn, and sum of all these forces. So that would be the total force on Q1. Now, if this is your origin, then this line is the position vector of Q1. We denote by R1, suppose, vector R1. The position vector of Q2, suppose we denote by R2, vector R2. Position vector of Q3, suppose we denote by vector R3, and so on. Position vector of Qn, we denote by vector Rn. Therefore, the net force on Q1, which is denoted by F1, vector F1, will be given by vector F12. Vector F12 means force on Q1 due to Q2 plus F of 1, 3, force on Q1 due to Q3 plus F of 1, 4, force on Q1 due to Q4, and so on up to F of 1n, means force on Q1 due to Qn. Now, according to Coulomb's law, we know that F12, force on Q1 due to Q2 is given by, according to Coulomb's law, K Q1 Q2 by R12 square, where R12 is the distance between the charge Q1 and Q2, and since I have written in vector form, so I have to represent by a unit vector, that is R21. Here also I can, where R21 is the distance between the charge Q1 and Q2. In general, I can write this expression as Fi is equal to K summation I is equal to 1 to n Qi Qn divided by Rni square with unit vector R and I in general. Now the next is continuous charge distribution. Continuous charge distribution. Extremely closed space charges forms continuous charge distribution. So when we talk about continuous charge distribution, we talk about three things. One is linear, second one is superficial, and the third one volumetric. So we talk about charge density. Charge density means charge per unit dimension. Now under this charge density, we have linear charge density denoted by lambda. Now linear charge density means charge per unit length. So linear charge density lambda is given by dq by dl. The second one, superficial charge density denoted by sigma. Now superficial charge density is charge per unit area. So the superficial charge density sigma is given by dq by dA. And the third one, volumetric charge density denoted by rho. So volumetric charge density is charge per unit volume. So the volumetric charge density rho is given by dq by dv. Let us discuss an application of Coulomb's law. We'll try to solve a numerical. So the question says, the electrostatic force of repulsion between two positively charged ions carrying equal charge is 3.7 into 10 to the power 9 Newton when they are separated by a distance of 5 angstrom. How many electrons are missing from each ion? Now, let us solve this problem. Here, the electrostatic force of repulsion is given to be 3.7 into 10 to the power 9 Newton. So the force of repulsion F is given to be 3.7 into 10 to the power 9 Newton. The distance between the charges is given to be 5 angstrom. So R is equal to 5 angstrom. Now, 1 angstrom is 10 to the power minus 10 meter. So 5 angstrom will be 5 into 10 to the power minus 10 meter. How many electrons are missing from each ion? So we have to find out n, the number of ions. Now, from Coulomb's law, the force of attraction or repulsion between the two charges is given by K, Q1, Q2 by R square. Now, the question talks about two positively equal charge. That means Q1 is equal to Q2. So in that case, F will be given by K. Since Q1 is equal to Q2, so Q1 into Q2 is also equal to Q1 by R square. Or F is given by K. Q1 times Q1 gives you Q1 square by R square. So, or Q1 will be given by square root of F times R square by K. Now let us substitute the values. Square root of F is given to be 3.7 into 10 to the power 9 Newton. R is given to be 5 into 10 to the power minus 10 meters. So R square means 5 into 10 to the power minus 10 holding square. By K is a constant, its value is 9 into 10 to the power 9 Newton meters square per Coulomb square. So as you simplify this expression, we get the result to be 3.2 into 10 to the power minus 19 Coulomb. Now in the last video, we have studied about the quantization of charge. So from quantization of charge, we know that Q is given by NE. In our case, we have taken the charge to be Q1. So Q1 is equal to NE. Or N will be given by Q1 divided by E. Now Q1 we have calculated as 3.2 into 10 to the power minus 19 Coulomb. And E is the charge of one electron. So the charge of one electron is 1.6 into 10 to the power minus 19 Coulomb. So as 3.2 divided by 1.6 gives you 2. So there are 2 ions missing from each of the charge. So there are 2 electrons missing from each ion. Now let us solve another problem. Let a charge Q on a body be divided into 2 charged bodies, and these bodies thereafter are kept at a certain distance from each other. Show that the force between the bodies is maximum if Q by Q is equal to 2. Now, Q is given to be the total charge, and this charge Q is divided into 2 charged bodies. So this charge capital Q is divided into 2 charged bodies. So if we take small q to be the charge on one body, then the charge on the other body will be capital Q minus small q. Now from Coulomb's law, we have F is equal to K product of the charges, that is Q into capital Q minus small q, divided by, if the distance between them is r, so it will be given by r square. We can rewrite it as K by r square, capital Q into small q minus small q into small q square. Now we will differentiate it with respect to small q. Now differentiating with respect to q. So differentiation of F with respect to q will be dF by dQ. Now K being a constant, distance being a constant, it's independent of differentiation. So we will differentiate capital Q into small q minus small q square with respect to small q. So this gives you K by r square. Now capital Q being independent of small q, okay, it will come out of the differentiation. So we are going to differentiate this small q with respect to small q. So dq by dq minus differentiation of q square with respect to small q. K by r square, here dq cancels out, so capital Q minus differentiation of q square with respect to small q will be 2q. Since differentiation of x square is 2x, okay, the same way differentiation of q square with respect to q will be twice q. Now we want to find out the maximum force, and we know that for maximum or minimum value, the first derivative should be equal to 0. df by dq will be equal to 0. You will be studying about this condition of maxima and minima in your calculus. Now df by dq is k by r square, capital Q minus twice of small q, and that is equal to 0. Now since k by r square cannot be 0, so capital Q minus 2q will be equal to 0. So from here, capital Q will be equal to twice of q, or capital Q by small q is equal to 2. So we get the condition. Now we want to check under this condition whether the force is maximum or not. Now we have already found the first derivative. Now if the second derivative is less than 0, then the force is maximum under the given condition. So let us see. We have already seen that df by dq is equal to k by r square, capital Q minus twice q. Now we have to find the second derivative. Second derivative means we have to differentiate this with respect to q again. So second order differentiation. So the differentiation of df by dq with respect to q. So d by dq of k by r square, q minus twice q. So this gives you d square f by dq square, second order differentiation. Now k by r square being independent of q comes out of the differentiation. Now capital Q being independent of small q, or if we differentiate this small q, capital Q with respect to q, okay, since capital Q being a constant, the differentiation of this q is 0. Minus 2 is a constant, so we'll differentiate this small q with respect to q. So dq cancels out. So what we have is minus 2k by r square. This minus indicates that the second order derivative is less than 0. Therefore, we are getting the maximum force. Therefore, the condition Q by Q equal to 2 is correct.